Okay, my name is Alexander Zaitsev. I am not Peter's brother, by the way. And I will be talking
He's
today.
my son.
Yeah. And I will be talking today about innovation, about what we're doing in Altinity with ClickHouse and data lakes. Look, this one doesn't work. What is Altinity? Altinity is ClickHouse shop. So we're first commercial vendor for ClickHouse since 2017, and still the main alternative to ClickHouse Inc. So we're doing ClickHouse development, ecosystem development. Eugene is responsible for a lot of ecosystem projects. And also we're trying to move ClickHouse to some new use cases that we see from our users. And I will be talking about one of such use cases today. But before then, let's talk about innovation. How innovation actually happens in the industry. It can be incremental when you add small pieces here and there and improve your products or improve user experience. It could be revolutionary when you came out with something completely new, which changes the way that how users do their business. Sometimes small incremental changes, they accumulate to the critical mass, and that leads to revolutionary change. This is mechanics. What is the source of innovation? You should listen to users. And what we're doing, we're always listening to users. We're trying to understand their needs, and that drives what we're trying to do. Of course, there are some revolutionary people like Steve Jobs that can invent something that everybody on the planet needs. But we know about Steve Jobs. We don't know about a million other people who try to invent something that didn't fly. So listen to users. And this is what we did. A few words about ClickHouse. I know that some of you know what ClickHouse is, and maybe more of you know after Eugene talks. But this is the analytical database for real-time analytics. It's not MySQL, it's not Postgres, it's not for OLAP. It's for scanning huge amounts of data for real-time ingest, for real-time queries. And it's very universal, it's very fast. It is built on columnar storage, vectorized engine, shared nothing architecture, and all kinds of stuff. And of course, it's open source yet. Internally, it's shared nothing architecture. When you have multiple ClickHouse servers, they could be separated as shards, as replicas. Every server has attached storage. And this is columnar block storage. So this is how it worked for 2 decades already, almost. And this is one of the problems of ClickHouse itself. So what is the problem? Problem is that storage is very expensive. Only one person in the room has more than 10 terabytes of data, but believe me, a lot of people who use ClickHouse has petabytes of data. And when you run petabytes of data, then storage is really, really, really expensive. If you have multiple replicas, then it is multiplies. So we have users in Altinity Cloud for whom storage costs are 80% or more of all the costs. So it is actually more expensive than compute because ClickHouse is so fast that you tend to keep all the data in ClickHouse, and you keep paying for that. So users want an object storage because it is 10 times less expensive in order to keep those petabytes of data. Otherwise, we'll go not to ClickHouse, but to some other technology like Staros, for example. So ClickHouse team, they of course added object storage, and there is a layer that we can use on below the ClickHouse, and it will keep ClickHouse data in object storage as well, but it will keep in this proprietary ClickHouse format, which is called merge tree. And when we're talking about petabytes of data, you usually don't want to access it only with ClickHouse. You want to feed some AI tools with this data. You want to feed some other applications with this data, and maybe not with ClickHouse only. So you want something different, and also when you have the data in object storage, it is still local to servers at some extent, or to your ClickHouse installation. If you have another team who wants to look at the same data, they have to go to the same ClickHouse instance. They cannot run different ClickHouse and look to the same data. This leads to another problem. So usually, your ClickHouse system is way over-provisioned for compute because you want to give resources to everybody who wants to use the system. So what users really want, they want to scale compute separately from the storage. It is called that compute and storage separation. If they need some more resources or new use cases, they just run more compute for that. And also they want to use it not just by ClickHouse, but some other tools, like Iceberg, for example, or some others machine learning tools. Now let's think a little bit about why ClickHouse is so fast. So ClickHouse is famous for speed, and it has a lot of different optimizations. Some of them are listed here, and it would took me several hours to explain how they work, but they were all designed with very smart people for speed. So every change in ClickHouse, it's always tested for speed. And if we want to change ClickHouse in a way how users want, they always ask, whatever you do, keep ClickHouse speed. It should be as fast as now or faster. Don't make it slower. So we have goals or user demands, object storage, shareable format, so we can share the data, not just with ClickHouse, but with other tools, compute storage separation, and real-time ClickHouse speed, so we need to keep it. How to solve this problem? It's not trivial. Let's look into merge tree. So merge tree is a table engine inside ClickHouse which stores data in columns. So in Postgres or MySQL, you typically store it in rows. There's Greenplum who can do it in columns, but this is a kind of exception. ClickHouse stores the data in columns, which makes it very efficient for analytical queries when you only pick up several columns from the table, and also it helps to compress data quite efficiently. We have people who migrated from Postgres to ClickHouse with 100 times cost reduction on storage, because data just it is compressed 100 times, thanks to columnar storage. But if you look into that, it's not just ClickHouse can do it. There is Parquet, which does exactly the same. It's not a table format. It's just open format, file format, which is totally open source and understood by many systems, and it can do exactly the same as merge tree does. Also, there is Iceberg, which is, so if you have files, Parquet files, you need to organize them. And there are tools to do it. One of them is Iceberg, which helps you to organize data on S3. It exposes this data as tables using so-called catalogs. And these catalogs can be used by many applications that connect to this data, and they see the same data. They run the same queries. It is open source, but it's not a database management system. It only can provide the information about the data, but you need a tool to query this data. So Parquet and Iceberg gives you almost everything. It is cheap, columnar, with partitioning, with a lot of features that databases may have, but it doesn't give you query engine at all. You may guess that what we're doing, we're trying to use ClickHouse as a query engine for Iceberg and Parquet. And this is what our Project Antalya stands for. So that was a source of innovation. Now we are trying to make innovation inside ClickHouse. We are extending ClickHouse native capabilities with some new features that allow us to use Iceberg and Parquet for shared storage. Additionally, on top of that, we are also extending ClickHouse to run stateless compute nodes, which we call swarms, that can be used in order to scale your compute for Parquet independently from your main ClickHouse cluster. So let's check those features one by one. So this is our swarm execution model. As you can see, the query on the right side, it goes to the initiator native ClickHouse cluster that you maybe deployed years ago. It contains some data. But when you need to query Iceberg and Parquet, you can additionally launch this what we call swarm cluster, which is stateless. It doesn't keep any data at all. Its only purpose is to fetch data from Iceberg, Parquet, S3 object storage in the most efficient way, do some pre-aggregation, and then return data back to initiator to provide final result to the client. It is totally stateless and new execution model. Sometimes I like one of the first slides on this, when you where the swarm concept goes from. So imagine there is a lake, right, with a lot of data, and you have a swarm of bees which just come into this lake. They take the water and bring to your ClickHouse gateway. And there is a man, a beekeeper, who is responsible for the swarm, just to manage it and make sure that nobody will come and kill it, right? How it works, so this is SQL, it's ClickHouse SQL, and you have a query that queries data from the public S3 bucket, and in order to extend it to Swarm, you just add a setting. You don't need to rewrite a query, just add a setting, and it will automatically offload a query to your Swarm cluster. So you don't need to do any changes to the main cluster, just offload data using settings. And similar for Iceberg, so this is how to configure Iceberg database engine in ClickHouse, and once configured, you can query it the same way. But in case of Iceberg, your tables in Iceberg, they look just as a regular tables in ClickHouse, but you can extend them to the Swarm as well with a setting. This is a very powerful execution model, very cool. But it doesn't work out of the box, so we had to add a lot of caching layers, because object storage, of course, is slower. If you have data on a local disk, it is very fast to read. If you have data on network, you need to go to network. And in object storage, you have a latency not just for streaming data, but also for connecting for the network, especially if your bucket is in different region. So we introduced a number of caching layers that help us to reduce this latency to very reasonable levels. And guess what? When in a simple performance test, and this is a setup, right? You have a data set of 1.3 billion rows, pretty common one, very simple queries. And if you run those queries on native ClickHouse and on Swarm, you can get performance on Swarm better thanks to additional compute that you can provision. So, and it will be even better with new ClickHouse versions because they introduce the better Parquet reader. This is a proof that with this architecture, we can actually make ClickHouse, keep ClickHouse performance, but use the different storage model based on open table formats. One more thing that we had to do is catalog. So catalog is a service which exposes data in a table format. And apparently, there are many catalogs, but not too many to run in Kubernetes. We only found one, Lake Keeper, which is quite popular right now, written in Rust, but all other options, they just didn't work. So we had to develop our own catalog, which allows us to deploy it in any Kubernetes environment, in our own cloud, in user environments. In this catalog can then be used as an entry point for external tools like AI or whatever, and for ClickHouse as well, for Swarm clusters. Next stage. So once we have this architecture, we need to think how to make it work better from ClickHouse. So you have some data in Iceberg, some data is merged. How to make them to look the same data for the end user. And this is what infinity table concept is for. This is kind of, you can imagine a super table, which is smart enough to understand that part of your data, maybe your recent days of data, are stored in a fast merged T tables, but your other data, your cold data, historical data, years of data is stored in Iceberg. And this infinity table, it automatically routes the query. ClickHouse already has such functionality internally that routes the query accordingly. Parts of the query goes to one storage, and another part of the query goes to another storage. And the results are merged and returned back to the user. And from the user perspective, there's no difference. User just queries the table, and all the logic is happening inside. And as you can see, the part of the query is executed in merged T on a local machine, but another part of the query is executed on a swarm of machines. Again, we are making it in order to make ClickHouse fast. And the next step, which is still in plans, we're working on that, is to implement double writes. We were talking about real-time data lakes at the beginning, and we will finish with that at the end. But in order, real-time is actually two sides of the coin. You need real-time queries, and you need real-time ingest. ClickHouse is very good for real-time ingest, but not Iceberg. In Iceberg, it is very, very slow, you cannot insert data too fast. That's why we originally were writing data to native ClickHouse, and then offloading it to the Iceberg. But we're also working on double write architecture that would write data in 2 storages automatically. And the infinity table, it already understands the semantic. It understands which data is hot, which data is cold, and can automatically select it in the query time. But in this case, we also have the real-time ingest, and the query is available immediately. But this is a data lake. In fact, this is a real-time data lake. We're real-time ingesting, and we're doing real-time queries at the same time. So this is what we were trying. We were not trying to build it, but eventually, after small increments addressing user needs, we ended up with a real-time data lake architecture, which is something really, really cool. This is all open source, so everybody can use it. If you're good with Kubernetes, you can run it. We have a GitHub repository with examples. There is a Terraform in order to set up EKS cluster in AWS. And everything else is managed by Kubernetes manifests. So you can apply, this is number of manifests, and it will stand up very trivial ClickHouse node and ClickHouse swarm cluster that you can use in order to run examples that I just demonstrated to you. So it really works, and we hardly worked to make it better. We also deployed everywhere using Altinity Cloud stack. I don't have time to talk about that in detail, but in general, what we can do, we can deploy the cloud infrastructure and Kubernetes infrastructure in any location, in any account. It could be AWS, GCP, Hetzner, DigitalOcean, but this part is not open source. It just makes things easier for users. Some resources that you can read if you're interested, and that's it. I try to be fast.